Now, what do you think that the average roll would be? All right. In other words, on average, what would the roll be? Now, if you remember from way back in the day when we found the mean, remember when we found the mean of frequency distributions? Remember what that was? The mean of a frequency distribution, assuming it's a population, and that's completely, if you think about it, we're going to be talking about this as though it's a population because it's really the set of all outcomes that are possible. It's not like I took a sampling of outcomes that are possible when rolling 2 dice. All right. So remember from the frequency distribution, what did we do? We took what was it? It was F times, remember, X with the midpoint, and then we divided by N. All right. Well, watch how cool this is. I can actually build out the frequency, or excuse me, the mean of a probability distribution from this definition. Check this out. It's so easily done. If I put F divided by N, isn't that the definition of probability? So I don't have any sort of midpoints because I'm not talking about class values. I'm not getting a roll between 1.5 and 2.5. I can only get a 2. I can only get a 3. It's not as though the die is going to balance on an edge or on a point. So I could rewrite this as the sum of X times F divided by N. Well, or excuse me, that should be a capital N. F divided by N, capital N, F divided by N is the probability. So I end up with X times P of X. Whoa, that's pretty cool. So the mean value, the mean roll that you would get when rolling 2 die is going to be the sum of this times this, plus this times this, plus this times this, etc., etc. Not only is that true for this probability distribution, but it's true for all probability distributions. You might want to memorize this guy. Okay? Now, I'm going to let you guys use some notes on exams and things of that nature, and we'll negotiate, excuse me, for what you're gonna be able to use. However, I do want you to be able to have these at your fingertips. So again, just fire yourself off a little note card. You know, it's like memorizing vocab, like anything like that. Hey, let's figure out what the average roll is real quick. So the mean of this guy is going to be, well, all I'm going to do is add up this times this. So 236 plus 636, that's 3 times 236, plus 1236 plus 2036 plus 3036 plus 4236, and then I can go down again, can't I? Whoa, I can actually, because the value is different. I get what, 36 plus 36. I do go down, but I don't, it's not symmetric. 36 plus 36 plus 22, 36 plus 12, 36. If I throw that in my calculator, if I do it by hand, I get 252, sorry about the margin, 36. That looks a little funky. If I throw it in my calculator, guess what I get? 7. The average roll, excuse me, the average roll with 2 die is a 7. It's the one that occurs the most. It is at the center of the distribution, literally as well as mathematically. Okay? I wonder why the casino makes it so that you quote-unquote crap out, or it gets to collect all the money when a dice player rolls a 7. Now, I'm going to show you another one that let's just roll 1 die, and we're going to do exactly the same thing. So instead of rolling 2 dice, let's roll 1 die. All right? Well, we got X, and we got P of X. And this one's a little easier, right? Because I can only roll, that's pretty good, 1, 2, 3, 4, 5, and 6. So if I throw these guys in, this one gets super simple. We know that the probability of all of these is 1/6. 1/6. They're all 1/6. Whoops. So if I want to find the mean for rolling 1 die, what is the average value when I roll 1 die? Well, look at it. It's 1 plus 2 plus 3 plus 4 plus 5 plus 6 all over 6. 1 times a sixth plus 2 times a sixth. I just found the common denominator, right? Let's see, that's easy, right? That's half 3, 21 sixths, 21 sixths, which is 7 halves, or 3.5. Now sometimes I get students and they're like, wait a sec, how can you have a roll? How can you have an average that isn't even rollable? In other words, it's impossible to roll a 3.5, right, with one die. It's not like if it lands on its edge and it sticks there, if it falls in a pile of sand and it sticks on its edge, that you've rolled a 3.5. You've either rolled a 3 or a 4. But think about that. We're not afraid of that. Averages work out that way all the time. If you think about the average number of kids that the traditional American family has, is like 2.7 kids. You can't have 7/10 of a kid. It represents an average. Over the course of many rolls with one die at a time, if I add up all those values and I divide by the number of rolls, I will come up with, after many rolls, a number very close to, if not exactly equal to, 3.5. So we're not afraid of that sort of a number. It doesn't have to be, even if our random variable is discrete, there's absolutely no reason that our mean is going to be a discrete value either. In fact, it very rarely works out that way. It's special in the 2 dice case, but like I said, it very rarely works out that way. Now, I'm going to give you the variance of these guys real quick. And again, don't freak out when you see this formula. I'm going to give you one that, let me just write them down for you. All right, so I'm going to take x minus mu, and you can actually see why this happens times p of x. All right? And then this is actually the formula. Now, remember back here when we came up with the mean? We got this mean from a frequency distribution. Now, we haven't gone into it much in this class in terms of trying to figure out how to find a variance in a frequency distribution, and we won't. But you can kind of see where this works out. Remember, probability is f divided by n. We've seen this before with variance. We're not afraid of this x minus mu thing. All right? So this is a real good way to understand how to find the variance of this guy. Remember, variance is what? Think about that. It's a measure of spread, it's a measure of variation, and it's also the standard deviation squared. However, and again, this is an introductory statistics class, so we're not going to go hugely into where these formulas are derived from. So you're going to have to take it a little bit with a grain of salt. There's an easier way to do this computation. Check it out. If it's the sum of x squared times p of x. To be honest with you guys, I don't remember these formulas if I can avoid it. And then all that I do is I just look them up when I need them. All right, because a calculator can spit them out. There's lots of ways to do this. This is an easy way to understand it theoretically. This is the easiest way to do it computationally. Okay, excuse me. I'm going to do the variance for the die, for a one die roll. We'll do that right now, just so I can show you. Okay. Now, what I'm going to do is I'm going to add, notice with this formula, I need the sum of x squared times p of x. So what I'm going to do is I'm going to add an x squared right here. Let's stick x squared right in here. So we're going to drop this down. I'm going to get a 1, a 4, a 9, a 16, a 25, and a 36. All right? Now, let's do this just a little bit at a time. We'll take our time. So this is going to be the sum of all of these x squared times their appropriate probabilities of that. So x squared times p of x. So that guy right there. So I'm going to get 1/6 plus 4/6. I'm going to not reduce it just because it's easier to do the mathematics. What is this? Plus 9/6 plus 16/6 plus 25/6 plus 36/6, right? That's this right here. And then I'm simply going to subtract out 3.5 squared, or 7/2 squared, by the time I'm done. All right, now let's see if we can do this thing in our head. There's 10, there's 20 for 30, 55, 85, 91. So I got 91/6 minus 49/4. That sound right? So what? 182 minus, oh God, 150, 147 147, 147 twelfths if I find a common denominator. Double check that to make sure I didn't do anything stupid. Let's see, 3, 120, yeah, 147. So what do I have here? 35, this is 35 twelfths, right? 35, yeah, looks good to me. Now, this is the variance, but remember, the standard deviation, sigma, is going to be the square root of the sum of x squared times p of x, right here, whoops, minus mu squared, that's this guy, which in our case is going to be the square root of 35 twelfths. Now, think about this. What's the standard deviation going to be? It's probably going to be relatively small because all of our values are between 1 and 6. They're uniformly grouped between 1 and 6. So let me throw this in my handy-dandy calculator because I'm good, but I'm not that good. Let's see, 35 divided by 12, and I'm going to get, let's see, booyakasha, I get approximately 1.71. Well, there you have it. That is the standard deviation of a one die roll. We will get an average of 3.5 on every roll, excuse me, with a standard deviation of 1.71. Now, let me show you something. This is kind of cool. Remember our rule about unusual, quote unquote, unusual rolls or unusual outcomes. And remember, once we had standard deviation, outcomes, we had a great way of sort of defining that. If I take the mean, which is 3.5, and I add 2 times the standard deviation, I get 1.71, right? So this is going to be 3.5 plus what? 3.42 approximately. I don't know exactly. And I'm going to get a 6.92. So if I get a value when I roll a die that is greater than 6.92, I get an unusual roll. Well, I'm only rolling one die, right? It's going to be, I can't roll a 6.9. I can't roll a number bigger than 6. Same thing, if I go 3.5 minus 2 times 1.71, right? Then this is 3.5 minus 3.42, and this is 0.08. If I get a roll that's less than 0.08, it's unusual. Now, think about this. These probabilities are uniformly distributed. In other words, everybody's got the same probability. So there better not be such thing as an unusual roll, or all hell is broken loose. Unlike over here, there may or may not be. Maybe a 12 or a 2 is an unusual roll. We could go through the process if we wanted to. It takes a long time, though, unfortunately. Excuse me. We can go through the process of figuring out what the standard deviation is of this guy, but I'm not going to subject you to that sort of pain. All right? Those rolls, the 2 or the 12 with the 2-die roll, may be considered quote-unquote unusual, but when I've got every outcome having the same probability, I better not get any unusual rolls, or something has gone horribly wrong. All right? Well, that gets you where you need to be as far as the brick and mortar. Remember, mean, standard deviation. Those are our buddies when we're talking about probability and statistics. That's where everything starts. Hopefully this was helpful. We're going to talk about expected value here in just a second.